Grayson, I think I'll proceed with the introductions at least. Meanwhile, I can see the attendees are joining in. So hello and welcome everyone to another Be Waste Wise webinar this month. And I'm Akanksha Singh. I'm the community builder at Be Waste Wise. We're a non-profit organization and we've been bridging the global expertise waste solutions expertise gap for more than 10 years now. And if you see the value in making the diverse sustainability dialogues such as these available free of charge to anyone and everyone, then please support us in our mission. We encourage you all to please check out our website and donate. We will also share the link to the donation page over the chat as well. Now let's move on to today's topic of discussion. This webinar will primarily discuss a recent ebook titled Battery Circularity: Powering a Sustainable Energy Future. We already shared the link of this ebook in the chat section as well. We are excited to have this ebook's authors on board today on our esteemed and as our esteemed panelists, Grayson Shore, Wyatt Green Williams, Neil Padukone, along with Dr. Laura Lander. They will discuss and highlight the key findings on how battery circularity, when integrated into urban infrastructure, can transform cities into hubs of resource recovery and clean innovation. Grayson Shore, co founder and chief product officer of Buckstop, will be moderating this session for us for the very first time, and we welcome and thank him for doing this for us. As I mentioned, he is also the co author of this report. Grayson is a battery and critical mineral circularity expert with over a decade of experience scaling multi-million dollar sustainability programs across 5 continents. He is also the founder and executive director of the Pacific Northwest Battery Collaborative, the US Pacific Northwest's largest network of battery professionals. Let me also provide a brief introduction on our panelists on this session as well, starting with Dr. Laura Lander. She's a senior lecturer at King's Department of Engineering and a UKRI Future Leaders Fellow. Laura's research focus aims to tackle the challenges of current energy storage systems to develop high performance sustainability battery devices. Along with Grayson, we have two more authors on board for this ebook discussion. Neil Padukone, Director, Green Economic Transformation at the New York Climate Exchange, where he leads the strategic efforts to build sustainable, inclusive green economy models in urban environments. And we also have Wyatt Green Williams, Community Impact Associate at Nine Dot Energy. Wyatt brings experience as a sustainability consultant, having supported Fortune 500 companies in implementing climate action strategies aligned with corporate sustainability goals. To know more about our speakers, we have already shared their LinkedIn profile. Please go through their profiles and you can connect and network with them separately. Now, before we proceed to this exciting discussion, there are a few important announcements. This webinar is being recorded and will be uploaded on our YouTube channel and on our website as well. Please use the Q&A function for your queries to the panel and use separately the chat function for all your views, your opinions, for sharing materials, for sharing insights related to the topic. As you can see, the topic is very interesting, so you can connect with the other participants as well on this chat section. So I'll not take much time, Grayson. Back to the panel and over to you.
Perfect. Thank you so much. Pleasure to be with you all today. I'm going to share my screen first, make sure we got that going before I jump in here. So let's see here. All right, showing the wrong screen there. Give me a second. It wouldn't be a Zoom call without some technical difficulties. So that's always part for the course there. All right, let's see. It should be showing the slides now. Yes, okay, I'm getting the thumbs up there. Perfect. Okay, and excellent. All right, so hello everybody. My name is Grayson Shore. It's a pleasure to be with you all here today. Big thank you to Be Waste Wise for organizing today's webinar and to my fellow co-panelists for joining today. We've been really excited about this presentation and put a lot of work into it behind the scenes. So excited to share some content with you all, and also especially excited to get into the Q&A. Kind of by run of show, I'm gonna introduce the topic for the next couple of minutes here. Then we're gonna jump over to Dr. Laura Lander, who's gonna give a more specific presentation on the EU context for battery circularity. And then we'll jump over to Neil, who's going to talk a little bit more about the report specifically. And then we'll jump into a Q&A with all four panelists. So at any point, feel free to start adding questions into the chat box, and we'll address as many as we can as we get into the Q&A session. But to start us off here, to give some context to battery circularity, I'm going to cover four topics very briefly. This is going to be a really quick run through. So forgive my quick speed of talking here. But again, we'll have chances in the Q&A to clarify things. So there's four topics I'm going to cover here briefly. First is the battery boom, talking about battery supply, demand, and regional trends. Secondly, talking about what are critical mineral supply chain risks from the US perspective. As I mentioned, Dr. Laura Lehner will be talking a little bit more about the EU perspective. Thirdly, battery chemistry. What do you need to know? And then fourth, circular economy solutions, recycling, reuse, and economic benefits. Okay, so let's jump into the battery boom first. So global battery sales have been growing year over year for at about 33% for the last 30 years, and sales have been doubling every 2 to 3 years. And this trend is actually starting to pick up in pace. As you can see in the slide here, the majority of demand historically has been, it's in the blue bar there on the far right, is for electric vehicles. However, this is starting to increase rapidly to include battery storage technology as well, also known as BESS or Battery Energy Storage Systems, BESS. These now account for about 15% of total battery deployments, up from 7% in 2020. And you can see in the slide here various countries. So we've got China and the US up top, showing where their proportional share of battery energy storage system deployment was. On the far left to where it's going in 2027, you can see a massive increase here over the next couple of years amongst all countries. But with great battery demand comes great supply demands as well. So in 2023, for example, batteries drove about 85% of lithium demand, 70% of cobalt, and 10% of nickel, according to the International Energy Agency. And so, what I think this is a really fascinating visualization of some of the supply chain complications associated with critical mineral and battery demand globally. So we might need as many as 283 new mines by 2030 to meet the demand for batteries and just critical minerals writ large. This is something that's quite concerning given the long lead times to bring on a new mine. It takes, on average, naturally, I'm going to pause here, just think in your mind, how long does it typically take globally to bring on a new mine in the world? So that's from initially starting to draw out the plans to when the material is actually like going on a conveyor belt and it's going to a facility from the mine. If you got the number in your mind here, it is 15.7 years global average. Now, think about what the US's average is. If you got a number in your head now, it's 20 to 29 years. It depends on the particular mineral. That number is actually decreasing though now, given some initiatives in the current administration, which has been cutting through some of the or reducing some of the permitting requirements in the U.S. But historically, the U.S. has been about the second longest amount of time that it takes to bring a new mine online globally. So much more than that 15.7 year average for the planet. So transitioning here, let's talk a little bit about China and the U.S.-China dynamic. We know from what we're seeing in the news quite regularly these days that the U.S. is quite reliant on China for its critical mineral supply, and again, these critical minerals going into batteries, but really to what extent? So let's jump into that. So the US is 100% reliant for 12 out of 50 of its critical minerals and over 50% reliant for another 29 of these 50. And China is the top producer worldwide for 29 of these 50 critical minerals. And just a quick sidebar, what is like a critical mineral? A critical mineral is defined by a country. It's kind of like a political term in a sense. A critical mineral is one country's critical mineral is different than another country's critical mineral. And so these 50 critical minerals that you'll hear me mention throughout the next few slides of this presentation is defined by the US government, but again, may be different from what other countries define as critical to their economy and to their national security. So jumping back from the sidebar here, in the U.S., although it produces only around 10% of the world's lithium, cobalt, or rather, in China, as though it only produces around 10% of the world's lithium, cobalt, nickel, and copper, it imports sufficient quantities to process around 65 to 90% of the global supply of these metals. So a way to think about this is China is basically the global processor for critical minerals, not necessarily the global source of these minerals. To put this in another way or another visual here, you can see in this graph it's showing various critical minerals and then also breaking down to the far right of different battery chemistries. We'll get into those in a few slides here, but LFP, NMC, and anode material for batteries, and then just batteries writ large. Orange is representing the global midstream and downstream supply proportion that China plays in that particular vertical there. So you can see writ large, everything on the screen here, China is the vast majority player in all of this. And I just point out too that if we step back and look at all energy technologies, so we look at solar, wind, hydro, nuclear, whatever it might be, we can see in the red box there at the bottom, the darker the dot, the more um, reliant the that particular horizontal box is. So for lithium, nickel, manganese, the more reliant that technology is on that mineral. So if there was a supply chain disruption, it would have a greater impact on that particular technology. So we can see for EV and battery storage, they're just across the board more at risk from supply chain shifts across all of its inputs. And so that gets into another important topic, which is export restrictions. There's a lot of words on this slide, but the main thing that I'd just like you to take away from this is that really starting in about 2022 and really more so picking up in the last year, we've started to see more export bans on the export of critical minerals, and many of those coming from China. You can see in the second column here, the majority are from China, but we've seen some from African countries, from other Asian countries too. And it is highlighted in recent years, especially again in the last year, how reliant the world is on really one country for these critical minerals. A good example of this is in April of this year, the Chinese government had introduced export controls on 7 heavy rare earth elements, a subcomponent of kind of these critical minerals. And in the EU context, you can see the blue dashed line here. The price of these minerals had significantly increased about 6x after these restrictions were put in place. While if you look at China at the bottom, their prices domestically had stayed just about the same. And so there's a lot of concern around the world that without diversifying these supply chains, there could be significant price risks to batteries and overall critical mineral supply chain as well. So jumping into our next segment here, let's talk about battery chemistry. What is NMC and LFP? So there's 2 major battery chemistries that are common today. These are not the only 2 chemistries, but for larger format batteries, these are the 2 most common. There's the one on the left, nickel, manganese, and cobalt, and the one on the right, LFP, is made of lithium iron phosphate. I'm going to jump through these slides rather quickly. Again, we can get into these more in the Q&A, but to profile these 2 battery chemistries side by side, this graph is a little bit warped, but the main idea to take away from this is the cycle life, the number of times you can charge and discharge over their lifetime. These 2 different battery chemistries is quite different. For an NMC battery, you're looking at maybe around 3,000 cycles. In an LFP battery, you could get somewhere maybe around 5,000. Depends on the temperature the battery is used at, how often you're discharging and how deep the discharge is. Are you bringing it all the way down to below 20%? Are you charging it all the way up to 100%? But roughly speaking, NMC has lower cycle life than LFP batteries do. From an embodied emissions perspective, the vast bulk of emissions from a battery typically come from the processing of the material. So we'll get into that in the next slide here. But if you were to take apart an EV battery, or rather an EV, and try to determine what's the emissions profile of that overall vehicle, the battery makes up somewhere between 40 to 60%. I would say that it's kind of trending down a little bit with the move towards lithium iron phosphate batteries. So we're looking at maybe a little bit more to somewhere like 30 to 50%. But in any case, the battery is typically the vast majority of the embodied emissions in an electric vehicle. Comparing LFP and NMC side by side, we'll see that NMC batteries typically have a higher emissions profile than LFP batteries do. And this comes in large part associated with the processing of the minerals within these batteries, cobalt being one of particular concern in the NMC batteries as compared to the LFP batteries, which don't have cobalt in them. I mentioned again this difference of LFP and NMC. LFP is really starting to become the major chemistry that we're seeing around the world, both for BESS, for battery energy storage systems, and also for especially electric vehicles. So around the world, we're starting to see this. China has really been driving forward this shift, but we're starting to see this become more common in Western countries as well, which have historically used more NMC batteries. All right, so jumping into our last segment here, talking about the circular economy solution. So we've talked a bit about how battery demand is rapidly increasing. It's led historically predominantly by EV battery demand, but that's also increased, or battery energy storage systems are also increasing demand share, and how battery production is carbon intensive. Its supply chain is also reliant really on predominantly one country. How can we reduce supply chain risks and lower battery life cycle emissions? I posit that the circular economy is the solution. Enabling and scaling the circular economy for critical minerals can lower the need for new mining activity by around 25 to 40% by 2050, according to the International Energy Association, or Administration rather, and reduce battery life cycle emissions by around 20%. So, but mineral circularity not only comes with environmental and social benefits, but also increases supply chain resilience and presents a significant financial opportunity to the innovators pioneering in this industry. So, cough, cough, wink, wink to the battery entrepreneurs and innovators out there. So, in the next few slides, I'm going to very briefly cover sequentially the potential positive benefits of recycling and reuse. So, for recycling first, using today's battery recycling technology, we can cover around 80 to 95% of the critical minerals in those batteries. And the market valuation estimate for recycling industry for batteries and critical minerals is expected to 5x by 2050 to reach a valuation of around 200 billion. I'll say as an asterisk to this, this number varies wildly across publications, and so, but in any case, they all show that it's increasing at multiples over the next few years. Battery recycling process, again, a lot of words on this slide. I'm just going to focus your eyes on the far right, those three tiles here. There's basically three main types of battery recycling: pyrometallurgy, hydrometallurgy, and direct recycling. I'd say pyro is what we're seeing traditionally as the majority of the share of battery recycling technologies out there that are deployed. Hydro a bit less, and direct a very, very small amount. Pyro, as the name kind of implies, is you're chucking batteries in essentially a large fire, burning those, and then taking the critical minerals out from the process. Hydrometallurgy, you're putting them in a chemical bath and getting the material out from that. And then direct recycling, you're physically taking apart a battery and pulling out material and processing it more or less by hand, or maybe utilizing some robotics. That's a gross generalization, but again, just high level overview here. From a system level benefits, just the main thing I'd like to point out from this slide is that if you look to the far right, and you look at the bottom lines here, there's a variety of benefits that come with recycling a battery. Not only would you see benefits from lower land use with less mining activity, but also things like carbon abatement and increase actually in economic and job opportunities, and of course, just overall carbon emission savings. compared to using virgin material. I'll point out here that from a recycling perspective, if you're a recycler, there's less value to be gathered from recycling an LFP battery. The market will, pay you less for the components that are in that battery as compared to an NMC battery. A lot of that comes from the nickel and the cobalt, which are more common in the NMC batteries versus the LFP batteries. The main thing to take away from this slide is that LFP batteries, from an economic perspective, lend themselves better to be reused as opposed to an NMC battery economically lends itself better to be recycled. So jumping to our last few slides here, reuse offers, I think, a more interesting and compelling pathway for battery circularity. A battery is typically considered fit for use in a new EV as long as it maintains 80% of total usable capacity and loses no more than 5% of its charge per day when not in use. How does this look in kind of a schematic sense? You could use your battery in its first life, maybe it's in an EV. After somewhere around 10, 15 years or so, that number can vary depending on how you're using the battery in the EV. You can repurpose that battery in a second life application. Maybe you take it out and use it as a battery energy storage system paired with solar or paired with wind. That could be maybe another 10 years of use. Then you recycle the battery. I'd say today we're predominantly seeing this middle step skipped, which I think is a huge loss because there's embodied emissions in that battery. There's still a lot of years left in those batteries, dependent upon, again, their quality or their state of health after their first use. So if it can be repurposed, it makes absolute sense, at least in my opinion, to repurpose them from at least a carbon savings perspective. Let's skip this slide for time. And lastly, I'll just say a reused EV battery can reduce the cost per kilowatt hour for a battery energy storage system by about 30% compared to using virgin material and have around 20% lower carbon emissions compared to utilizing virgin battery material. So with that, I'll thank you all. Again, a reminder to put any questions in the chat box there. And Laura, I'm going to pass it over to you.
Thank you so much, Grayson. Let me share my slides.
I'll confirm with you once they're up on that. There you go.
Is it
Yes.
working? Perfect.
And if you can jump into presenter mode, then they'll be there. You go. We can see your notes actually if
Then
if
it's also the wrong window.
no worries. Give you a moment for that too. Just checking Q&As. Excellent. Nice to see some questions coming in the chat box here already. So thank you folks for adding those in. And Laura, there we go. We can see it perfectly.
Good.
You're all good to go.
Perfect. Well, thank you so much, Grayson. And I'm following up on some of the points which Grayson also mentioned on the critical minerals and the supply chains, but this time more from an EU perspective. So I'm presenting a study one of my students conducted recently on the impact of the EU net zero strategies and specifically on the EU battery directive, which was recently updated on the battery supply chain and the battery costs in the EU. So Grayson already mentioned the big challenge of potential supply chain risks for critical battery materials, again, specifically also in Europe and Western countries where we rely heavily for battery materials on exporting countries. And of course, those bring risks with regards to the current geopolitical tensions, price volatilities, and overall our net zero strategies are really dependent on the mercy of other countries practically. And we need to find ways how we can strengthen and make our national supply chains more, kind of more independent. Here, a circular economy is becoming more and more important, really that we can keep the materials of batteries within the country and make sure that through recycling, through reuse, we really have our own little supply chain of those battery materials. So this has been recognized also by the EU, who introduced or updated, as I mentioned, the EU battery regulation in 2023. And they put a very strong focus on battery recycling and also introduced a minimum recycled content for every new battery which is placed on the European market from 2031 onwards. So for lithium and nickel, this means every new battery needs to contain 6% of recycled lithium and nickel and 16% of recycled cobalt. The question is now, whilst this is very commendable and the intention is very good. Do we actually have enough material within Europe and the UK to fulfill this mandate? Because of course, there's a huge lag between when we put our new batteries into market and when they reach end of life. So we need to take this into account as well. And the question is that we wanted to answer is recycled material becoming the new critical material, really? So we took a bit more academic approach, and we wanted to create a framework which allows us to assess the impact of policies, in this case, the EU battery regulation, but this can be really any policy, on the battery market and the battery costs. So we have this policy economic framework, how we called it, with 3 steps. So we conducted a material flow analysis where we tried to understand how much of recycled material do we have available and how much do we need to fulfill the mandate. What are potential price evolutions of critical materials, recycled critical materials, so lithium, cobalt, nickel. And here we had also a lot of interactions with industry representatives. We had a workshop where also Grayson was participating to understand how experts see the market trends. And then based on those materials price assessments, we wanted to understand how do the costs for actual battery cells and battery packs evolve in the future. So I'm just presenting very briefly the overall results. So we could see that recycled lithium, for example, is in a surplus, surprisingly, by 2030. Again, this is an EU perspective with EU data. However, recycled nickel and cobalt might not fulfill the demand, and there can be a lack of up to 85%. So to answer the question, do we have enough material? No, we might not have enough material under the current scenarios that we're seeing. So also this is taking into account the minimum recycled content. But what, for example, if OEMs decide to use more recycled content, which again is actually the way we want to push them. So BMW has announced that they want to use mostly recycled material in their batteries, for instance. So the demand for recycled battery materials will be even higher. And of course, the supply lack will be bigger. So we then wanted to check what does the supply bottleneck mean for the materials prices. So we did a kind of economic analysis based on virgin material for lithium, nickel, cobalt, for those 3 materials. I'm showing only lithium here as a kind of case. And we could see that starting, for example, from 2024, 25 onwards, recycled material, so this is here the blue line, could be more expensive than the base case, which is here the line with the squares, which is the virgin material price. So showing that the fact that we have kind of a supply chain bottleneck for recycled material can also mean that the price for recycled material can increase even stronger, for example, if we put a green premium on those materials prices, etc. So we then implemented those prices in a battery cost model, which is commonly used within the industry. And we could see that for battery packs, including lithium iron phosphate, nickel cobalt aluminum, which is, for example, also one of the Tesla packs, and nickel manganese cobalt, we can have cost increases for up to 13%, for instance, compared to a battery pack which uses only virgin material. So this definitely goes against the trend where we want to actually decrease the battery pack cost so that EVs become more cost competitive, and also to reduce the financial burden on the consumers. So yeah, this was bad news for us. Anyway, to conclude with this analysis, we could show that actually policies which have really good intentions and which we need to support and further implement can also have adverse effects if they're not properly analyzed on their future impacts on the wider economy. Another problem that we foresaw is that there's a loophole in the battery regulation where it's not clarified where the recycled material is actually coming from. So we are saying, of course, it should come from the EU because the main goal is to have a national supply chain. But in the battery EU regulation, they didn't specify this. So the recycled material could also come from Asia, for instance. So we would again have these kind of materials dependencies, just this time for recycled material. And also, how will consumers and the industry react to increase in battery pack costs? So this is also which would need to be assessed in more detail in the future. And with this, I would like to thank you very much. Sorry, I went a bit over time. But yeah, thank you for your attention.
Thank you, Laura. That was awesome. It's really striking to see how those well-intentioned policies can actually significantly increase not only the demand but also the price of battery material as well. So I think that really underscores the need to create more domestic supply chains for these minerals and these materials. So awesome. Thanks for pointing that out. Really awesome research. Perfect. Well, we will pass it over to Neil next. So, Neil, the stage is yours. And I'll let you know once we see your screen pop up there as well. Perfect. Yes, we can see the report there. All right, Neil, over to you.
Great. Thank you so much. Good morning, everybody. My name is Neil Padacone. As Akanksha had described, I'm a co-author of this report, along with Grayson and my colleague Wyatt. We recently released this ebook, An Introduction to Battery Circularity, at an event that we had organized during Climate Week, the Urban Battery Forum, in collaboration with the Global Battery Alliance. At that event, GBA had released the beta version of their battery passport, which is a really important tool for tracking the kind of full life cycle of a battery, both from the provenance of its materials to make sure that the materials were sourced from more responsible sources and could have a full life cycle that was trackable and traceable. But can also facilitate the future uses of those materials and of those batteries. And so that's a really important piece of the battery life cycle supply that contributes to all the conversation of every piece of this conversation, both that Grayson was discussing and that Laura was talking about, and its implementation in the European Union. But at that event, we also showcased a few we released the report, showcased a few cities that were doing really innovative things in the battery ecosystem, as well as showcased a few companies, particularly with a particular focus on circularity, whether second life uses, recycling, battery exchanges, which are an important piece of this, battery life extension, and their deployment at grid scale. And so the ebook itself, I'll just take a few moments to walk you through just a very high level of the table of contents, and I would welcome and encourage all of the participants to click through the full ebook. There's a lot of material in there. The first sort of half of it kind of goes through much of the content that Grayson had shared, the battery boom and the growth in demand here, what that means from a critical minerals supply chain perspective, the unique components of different battery chemistries, and then circular economy solutions. In addition to recycling and reuse, however, in this report, we also add a third piece, which is just extending the first use life of batteries. If the end goal is to minimize upstream demand on raw materials, on mining, and keep existing materials in play, in use for as long as they can, extending first use is probably the first piece of that. And so Grayson had described how electric vehicle batteries, particularly on the heavy duty side, they can degrade to about 80 or 75% of their capacity somewhere between 7 and 12 or 15 years, depending on their usage. However, if we can use data to optimize the life of those batteries, whether using data to analyze different routes based on the force they need to use to climb steep hills, the type of the weather that they exist in, and optimize the routes that they go on. Perhaps that 7 to 12 years can be extended to 10 to 15 years or even further. And in fact, in conversations that we've had with fleets around the world, many of the large bus vehicles, the bus batteries that have been in use, have actually had longer life cycles than one that they were anticipating, than the fleet managers were anticipating, and two that their insurers had also anticipated and planned to insure, which is a good thing from the perspective of battery life cycle. And so if we can extend the first usage of those batteries, of those primary assets, the better. And so we articulate in the report a few techniques for doing that. The second piece is, of course, as Grayson described, reusing and repurposing those batteries, taking out old electric vehicle batteries and repurposing them for building energy storage, for grid energy storage, and possibly even after diagnosing their safety, remanufacturing them for smaller usage, for micromobility, for street lamps, for a variety of other applications. And then finally, after those second repurposed cases are deployed, and those second life batteries come to another level of degradation, creating recycling ecosystems to make sure that those minerals and materials can be extracted and reused and recirculated in the supply chain, which would in turn, of course, minimize upstream pressures on mining. When we started this project, we were in a very different federal situation and context. And so that was the initial impetus for how we could take advantage in the United States, of course. And that was the initial impetus for how we could take advantage of this growth in electric vehicle usage and battery energy storage and grid storage, and in grid storage to support the deployment of renewables. In the middle of this report, of the writing of this research, there was a big disruption to the federal policies context. And so that made us think a little bit more about, without the same level of subsidy, without the same level of federal support for renewables and for the battery supply chain domestically, which in turn, of course, kind of has global supply chain implications. What would that mean for the development of battery economies? And so from our perspective, that actually, even though that did come with a tremendous challenge, which would be better for this market if those subsidies had not been reversed, there is an opportunity here for cities and urban areas to really step up and take advantage of the economic benefits, the climate benefits, and frankly, the technical benefits, the practical benefits of battery circularity. One of which is, of course, improving the economics of fleet electrification. Because if a fleet, if a bus or truck or car owner is able to sell their depleted battery to a next user, the economics make more sense of those upfront costs of electrifying in the first place. And so honing in on cities and urban regions for how these circular economies can develop, that really had a few implications. The first is just the scale of electrification in urban areas meant that the electrified fleets that do exist there and that really are preponderant in those regions can utilize those innovations in data management, but also to develop markets for pre-owned or used electric vehicles that remain relatively localized, and extend that the life of that battery asset in its primary use. The second implication is that as dense markets that are home to both the majority of electric vehicle deployments and are central players in energy storage deployments, metropolitan areas are really uniquely positioned to connect that forthcoming supply of degraded EV batteries with the demand from energy storage systems, and in effect create a very local closed loop market. And frankly, one of, to tip a hat to some of Laura's research around the economics of, these have to be economically viable, right? They have to be cost competitive with virgin batteries. And one of the big challenges for making second life batteries financially viable is just the transportation costs, because many of those, the transportation from an old electric vehicle to the diagnostic site to the remanufacturing site, those assets, those battery assets, become potentially hazardous materials, and the cost of transporting hazardous materials across those spaces can be tremendously high. And if you are shipping those across countries, across regions, across globes, the transportation costs really skyrocket. And so if you can keep those at a local, regional level, you reduce those transportation costs and improve the economics of circularity. And then finally, after the full electric storage value of battery assets has been extracted, municipalities can work in cooperation with regional, state, and other entities and private entities, of course, to develop recycling facilities within the region, which would similarly minimize transportation costs in that material recovery. So we conclude here with some examples and some policy ideas, including extended producer responsibility laws, which kind of incent the market to think about all of these possibilities, and also encourage the development of responsible battery buyers alliances of private and local government battery users, including fleets, that can informally align on purchasing guidelines, on analytic sharing, on design and transportation requirements, and circular design, so that there is a nudge to upstream suppliers to develop new battery assets that facilitate circularity in the broader market. So forgive me, I think I've gone a little over time, but I will pause there.
Awesome. Thank you so much, Neil. Good comprehensive overview of some of the key points in the ebook. So thank you for introducing that. And I believe Kansha also put a link in the chat box to the report as well. So it's free to download. Please read it, enjoy it, share it. Knowledge is a gift. So that's why Neil, Wyatt, and I, and also with Laura's contributions to the report at various points, had pulled together this and written this report, is to increase awareness on this topic. So please do check out the report. All right. Well, with that, we are now officially into our Q&A portion of the session. We have 15 minutes here and a good handful of questions. Thank you for all the questions that have already rolled in. We've answered a few of them in the Q&A box. So if you haven't already, check out those written responses if we're unable to get to all of them live. But I first want to pass a question of my own first. I'm going to use, as they say, moderator privilege here to ask a question of my own before we jump into the Q&A. And I'm going to pass the question over to Wyatt. Wyatt, you've in part grown up in Jamaica. And of course, Jamaica just witnessed a pretty sad and horrendous hurricane, a lot of destruction that happened there, which had impacted the grid and access to energy and what have you. I'm curious, what do you see as the role of batteries for energy resilience, and where do you see the topic of battery circularity playing into such situations?
Thank you, Grayson. Thank you, B-Wastewise, for having us and allowing us to talk about this report and Laura's work more. It's a tremendous platform. Grayson, on this question, just a little bit more context. On October 28th, Hurricane Melissa, a Category 5 hurricane, hit Jamaica. This hurricane completely devastated the western side of the island. It had the highest wind speed ever recorded at over 250 miles per hour, which is over 400 kilometers per hour. And many people have described it as basically enduring tornado speed winds for between 3 and 4 hours. And this led to utter devastation of physical infrastructure. So any houses that were not made of concrete or cement, which were a majority of the houses in western Jamaica, were were at least partially damaged, if not totally destroyed. And this also devastated the public energy infrastructure. So the transmission lines, the generation plants um, have uh, have been destroyed, and there is no power in Western Jamaica currently. This is being restored based in the city centers, but batteries and distributed energy resources can be an important part and mode of this recovery. Um, Personal testimony is I know that the places that still have power are the ones that were equipped with solar. We're able to engineer them in a way that they endured the storm, and now are often places of resilience within communities that are powering things like Starlink and allowing communication. And so in the future, Jamaica should, because of its wealth of solar resources, the amount of sun it gets, and the difficulty in maintaining these transmission lines, invest into batteries and microgrids. But at the same time, it's not equipped with recycling facilities. And so there is an important considerations into how reuse can play a role, or the management justly of these wastes that are generated, so that they aren't placed or shipped in ways that they're informally captured and recycled to environmental and health degradation, which is often the case. Um, but we'll see how it goes. I think everyone's first priority is making sure that people have water, food, and shelter in the next weeks. And these power recovery and the development of other types of systems are going to need some policy changes based on the current policy framework of Jamaica, which I think is a little bit out of our scope for today, but shows the potential of these technologies to play a role in sustainable development of these, especially in the recovery after catastrophic events like Hurricane Melissa.
Appreciate that overview there, Wyatt, and also giving kind of a good case study of how batteries can be deployed, including repurposed batteries in areas to ensure grid resilience. So I appreciate that, and good, kind of example too with utilizing them for linking with Starlink and things of that nature. So excellent. All right, well, jumping into our Q&A box here. Our most upvoted question that we haven't answered yet in writing is by Chaz Street. And the question is as follows: how can we fight a lithium-ion battery fire without using PFAS containing fire suppressants? PFAS are those forever chemicals you may have heard of in the news, which have been linked to some to cancer and things of that nature. Let's see, Laura, do you want to tackle this question?
I can try. I'm not a kind of battery fire suppressant expert, but from what I know is that suppressing battery fires is very challenging, and there's no standard across firefighters, I want to say. There are different ways that, for example, I saw some cases where they just let the battery burn out, really. Other kind of water-based suppressants you can't really use because you have an electric system, so this is even more dangerous. So to be honest, I'm not able to answer that question probably to a satisfactory level. But I know that there is research going on how we can control and suppress battery fires, also in ways that are not toxic, because often you have gases that are formed during battery fires, which when they react with the fire suppressant can also form other toxic gases. So I think it's a very complex chemical system in itself.
Excellent answer. Wyatt, over to you.
Yeah, just adding on perfect encapsulation of the current industry trends. And this tactic of letting fire burn is particularly bad for the visibility of systems. So, for example, Moss Landing, California, was the largest battery fire ever, and the tactic that is currently adopted for fires is as Laura battery fires is as Laura described, just to let it burn, because often the introduction of water or other fire suppressants can make the conditions of the chemical in these batteries worse. And I'm going to plug a group into the group chat called the Energy Response Group, which has done a lot of good research and the firsthand reports on battery fires and showing the or lack thereof impacts in air and water quality after fires such as these.
Excellent point there, Wyatt. And Neil, over to you.
Sorry, don't want to spend too much time. I don't have enough time, but one point I'd add is maybe a bit of a cop out here, but a way to minimize fires is to focus on kind of the upstream piece of it. At least focusing a little bit parochially. A lot of the conversations we've had with the New York fire department in New York is to make sure that the batteries that are entering the marketplace in the first place are of high enough quality that they are not starting those fires. The big problem in cities and dense cities has been e-bike fires. Battery energy storage systems have not experienced anything of that sort, precisely because they're so highly regulated, and it's made sure that there are not the types of risks that these batteries could experience aren't entering the marketplace. On the e-bike side, most of the assets that are entering the marketplace and that are causing these fires that in many cases wind up having tremendous consequences are largely because they are either unregulated or kind of jury-rigged to be faster, precisely because they haven't had the oversight. And so some of the ways that local authorities are trying to clamp down on those are encouraging battery swapping so that poor quality batteries can be taken off the market entirely in exchange for a free regulated battery.
Appreciate that response there, Neil, as well. And Chaz, thanks for the great question. Elicited some good discussion there. I'd add one last point on, which is, according to research, battery fires, if you factor in kind of like a per capita, so number of batteries that have been deployed, lithium-ion batteries that have been employed, has actually dropped precipitously. I think it's by somewhere like 80% plus over recent years. And this is in part because of new fire suppression technologies built within batteries that reduce what's called thermal runaway. Essentially, that's when a battery may catch on fire or explode, so to speak. It's going through a thermal runaway. And that those number of batteries as a proportion of those that are deployed has again been dropping precipitously given new advances in technology within these batteries and the systems that are around them when they're deployed. So in short, batteries are getting safer and safer. There's been some really good questions in the chat box here, both in the Q&A and then also the webinar chat box about lead acid batteries and concerns around exporting batteries to other countries for processing and maybe some environmental concerns that come along with that. I wanted to open up to the panel here. There's a handful of questions on this, so just curious if you could address kind of generally what you're seeing in the supply chain on the back end for batteries, both lithium ion and lead acid, and any of the kind of those environmental concerns that go along that, and any key thoughts that you'd want to share on that front. Maybe Laura, if I can go over to you first. There was even one question about the EU exporting some of these batteries to places like Africa. Curious if you have any thoughts on the topic.
Yeah, absolutely. So first of all, to say lead acid batteries are very toxic, and this is also why they are one of the most recycled kind of batteries ever. I think it's over 90%. It's a big problem that we export, like that batteries get practically lost being exported to countries where we can't really follow them anymore. We can't regulate what's going to happen with them. And also we can't monitor the conditions under which they're being treated in those countries. And it's not only recycling, it's also, of course, on the mining side where we have similar problems. And I think what is really important is that the local governments implement very strict policies on this and really monitor, maybe together with recycling industries, materials processors, to see that the working conditions there are being respected, and also that the safety conditions for labor, for workers, but also for the environment are being followed. I think it's a very big problem, yeah.
Thank you, Laura. Good points there. And Neil or Wyatt, anything to add on that front? Yep, Wyatt.
I think Laura captured it. It's also that lead acid batteries are a more mature technology in that they've been in these markets and people are familiar with how to recover, reprocess, reuse. And unfortunately informally recycle these technologies. It's likely that lithium-ion batteries will get to the same place, but there is tremendous danger here because these are stores of energy that are often more dense and difficult to process. And so it's much more important to have formal avenues for recycling and processing that mitigates the environmental and health hazard again. And enables reuse, which is a tremendous opportunity with this technology, as highlighted in Grace's presentation and in this ebook.
Awesome. Thank you, Wyatt. I'll add just one point too, pulling from a side discussion that's been going on in the webinar chat box. Lead acid batteries are, well, let me actually take it a further step back. There was a very interesting report that came out by the New York Times, which was talking about recently, that was talking about the lead acid battery recycling supply chain and the pollution that's associated with it in countries like Nigeria. And the number one comment that I saw out of the 550 plus comments on New York Times website for that article was about lead acid batteries being or not being in electric vehicles. And just to clarify, lead acid batteries are still in electric vehicles. They're in internal combustion engine vehicles as their sole battery, and then also within electric vehicle batteries or within electric vehicles to serve as a battery for things like the lights in a car, like when you turn the light on the driver's side to read something or what have you. So there is still some concern about EVs contributing to that potential pollution there, in addition to the internal combustion engine vehicles. We're in our last about 90 seconds or so here. We've answered 7 questions in the chat box here. We've covered 2 or about, I would say actually about 3 or 4 of the questions that were not written verbally. We've covered those. So I want to wrap us here just so we make sure we end on time. And I'm going to pass it over to Akansha to wrap us up here. But I just say, for those of you that we didn't get to the questions, thank you for asking the good questions. Neil, Wyatt, Laura, myself, we can all be reached out to via LinkedIn if you'd like to connect. Drop us a line there. More than happy to chat. Really appreciate your attention today. Again, the good questions, the good dialogue. And I'm going to pass it over to Akansha to wrap us up from the Be Waste Wise side. And just again, many thanks for organizing and hosting today's webinar.
Thank you, Grayson. Thank you so much to our panel today as well for taking time out. And it's hard pressed, so we will not take much time. As you can hear from our panelists, the ebook is free to download. Please go through the link, download, and see through whatever is being talked about here on this panel. We are very glad that you all use this platform to share your informative insights. We can see that the networking was done and a lot of queries were answered. Few queries which were not answered, we'll make sure that we'll be passing on to our panelists as well later on. As I mentioned, that this webinar is going to be recorded and will be available on our YouTube channel and on our website. If you like to stay updated on our social media website, on our social media links, please go through all the upcoming webinars or the topics you can suggest. Thank you all and have a great day ahead.
Thank you, everyone.
Thank you. Thank you so much.
Thank you, Grayson. Thank you, Neil. Thank you,
Thank
Dr.
you.
Laura. What? Thank you for your time.
Thank you for
Thank
having
you.